video for 8.3 volumes, and this is actually the last section that we're going to cover in chapter 8. So I do want you to read over page 406 in your textbook, whether the physical textbook or online. This gives you a really nice overview of solids and why we take the volume of solids and how we can look at cross sections to help us with that. So the volume of a solid of known integral cross-section area A of x from x is equal to A to x is equal to B is going to be the integral of your A from that A to B value. So just like with position, velocity, acceleration, how when we integrate acceleration we get velocity, when we integrate velocity we get position. Because volume is to the third, area is to the second, when you integrate area, you're going to go up by one dimension, so integrating area is going to give you volume. So this is the basic idea behind this entire section, is you're going to figure out what the area of your cross-section is as some type of equation, and then when you do that integration, it is going to give you the volume. Now, in many cases, we're actually going to be taking some type of line, and we're going to be rotating that line. And when that happens, you're typically going to have some type of circular shape as your cross-section. So that is something to keep in mind. We are going to be doing a lot with areas of circles. You will have some areas of some squares and possibly some rectangles and some other things like that. So here is your steps for finding your volume by slicing. So you're going to sketch whatever and what a typical cross-section would look like. You need to determine whether your cross-section, again, is a circle, is it a triangle, is it a square, because then step 2 is find a formula for A of x. So you need to know, am I looking for the area of a circle? Am I looking for the area of a square? Am I looking for the area of a semicircle or a triangle or something similar? You're going to find your limits of integration. So you're going from what to what, and then you're going to integrate your A of x to find the volume. So that leads us to example 1. It says a pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the pyramid parallel to the base is a square. So it does already tell me what my cross-section is. So in this case, I know my cross-section is going to be a square, and I want to find the volume of a pyramid. So I've kind of drawn this on an angle, and I'm going to sketch this off here. Imagine this line is going down through the pyramid. I'm actually going to lay the pyramid down instead of sitting it up, because it's a little bit easier to sketch the cross-section here. So we'll see how this goes. Okay, so there's my 0. So I have this is coming out here, and then we are going, this one is coming out here. I'm going up there. This one I think is going to have to go out a little bit further. I have a really beautiful picture of this in my notes. And this one, it's a little bit off. Let's try that again. I know I can do that a little bit better. Bottom one isn't too bad, but I'm not happy with how the top one looks. So we'll have this, and then that, and then that, and then we'll go like that. Okay, so that looks a little bit better. And we can have this coming. This is basically going to be reaching down here. So that is going to be your 3. And so then when I look at my cross sections, so that means that this distance is 3. Each of these sides is also 3. But if I were to slice this at any point, so that's coming up there, that's going down there, and it's going to look like that. If I were to slice that, that cross section is going to be a square. Well, this side is x and this side is x of your square. I know it can't be 3 unless I'm not really slicing, but just looking at the base of it. And I know it's not going to be 0, but 0 and 3 are actually going to be my bounds. So step 1, there's your sketch. Step 2, your area is a square. Now I don't know any other information about that, so that's why I had to let each side equal x. It is a square, so they are exactly the same. And that means that my formula is going to be x squared. 3, my limits are going to go from x equals 0 to x equals 3. And then finally for number 4, I'm actually going to integrate. So that's from 0 to 3 of x squared dx. So that's going to give me 1/3 x cubed. And then from 0 to 3. So it's 1/3 of 3 cubed minus 0, because when I plug in 0, I'm just going to get back 0. So 3 cubed is 27. 1/3 of that is going to be 9. And it does give me my units as meters. So that's 9 meters cubed is going to be the answer for my volume. With volumes, because they are in the 3rd dimension, all of your units should be to the 3rd power. And that brings us to example 2. It says the region between the graph of f of x equals 2 plus x cosine of x and the x-axis over the interval -2 to 2 is revolved about the x-axis to generate a solid. Find the volume of the solid. So I know I'm going from -2 to +2. Those are going to be my bounds that I'm going to use for my integral. I need to do a sketch here. You will have to use a graphing calculator to figure out what this curve looks like. Make sure you're only looking between -2 and 2. And if you look at this, it actually looks something like it's like this, and then it comes down like that for where it stops. So I'm going to be taking that, and I'm going to be revolving that about the x-axis. So I'm going to be swinging it out. Think of this as a sheet of paper. And I'm going to undo this here in a moment. So you're taking this sheet of paper, and you are swinging it out. I don't know if you've ever seen those decorations that come flat, and then you fold them out, and they become like these circular balls of paper. That's almost what you're going to be thinking about with this. So I'm going to be taking this, and I'm going to be swinging it around. So if you're going to sketch that, the easiest thing to do is to graph the mirror reflection down below the x-axis of what this is going to look like. So I'm going to have something kind of like that. See how it's the mirror image of what's going on there? And so then whenever I look at this, anytime you're swinging something around like that, it's almost going to be making this like base type shape. So if I look at a cross section of that, it's going to be a circle. So my cross section here is actually going to be a circle. And I know it's not completely even. It actually looks like I might want to move this line up a little bit to make it a little more even. That looks a little bit better. So step 1 is my picture. Step 2, I know I'm going to have a circle cross section, but I also have to come up with the formula for that. So the formula is going to be pi r squared, but my r is going to represent the height there. Well, from the x-axis to the curve, that's going to be my formula, my equation that I have. So that's pi times 2 plus x cosine of x, and then the quantity squared. Number 3 then are my bounds. Well, that's going to go from x equals -2 to x equals +2. And then 4, I can actually set up my integral, and I can find my solution. So I have pi times my r squared. This is not something you can integrate by hand. The x cosine x does pose a problem with that. So you would want to use the graphing calculator. I'm not going to pull up the calculator and go through that, but if you do need some help going through that math, please let me know. But when you do this on the calculator, you actually get 52.429 units cubed. It doesn't give me, like in the previous one, it said meters. This one does not say anything about that. So this one is units cubed. The last example we're going to look at in this particular video deals with a similar type of region. It says region in the first quadrant enclosed by the y-axis and the graphs of y equals cosine of x and y equals sine of x is revolved about the x-axis to form a solid. This one is going to be a little bit different than what we looked at before, and you'll see that once we get this sketched out. So I'm going to graph my cosine of x. Cosine of x, here's my 1, my -1. So cosine of x is going to come down kind of like that. Sine of x comes through the x-axis and comes up like that. So I'm actually going to get rid of all of this excess stuff because I know that I'm bound by the y-axis. So there's my y-axis. That means one of my x values is going to be 0. And then I do have this intersection point here for the other one, which in the first quadrant, cosine and sine are going to be the same value at pi over 4. So I know that that x value, I guess I'll put that down there instead of up top. Pi over 4 is actually going to be where they cross. So if I take this and rotate it, of course I have this one, and then I have this one. Well, if I'm taking a cross section of this, notice that whatever I do is going to have a hole in the middle. This is called the washer method because I don't get a disc like I did in example 2. I get a washer, so it's a circle with a circle cut out in the center. You can still find the area of this. The key is just going to be, it's the area of the bigger circle minus the area of the little circle of the inside. So 1 is going to be my picture. 2 is the fact that I have a washer. So this is going to be pi of the big R squared minus pi of the little r squared. Well, the big R squared, the one that's on top, the outer one, the blue one, is my cosine. So it's going to be pi times cosine squared. And then the little one is sine. You know, it kind of ran out of space there. Hopefully you can still read that. So the inside one is going to have, the inside one has sine as its radius, and then the outside one is going to have cosine as its radius. My bounds then for number 3 are going to go from x equals 0 to pi over 4. And that's what I'm going to be integrating. Because both of these have pi's in them, I can actually pull that pi out. Oh, and I didn't pull the pi out like I said I was going to. So I can put the pi on the outside there and have this be cosine squared minus sine squared. Now, there is a relationship here between these two. We can't integrate these as they are, but we can do a substitution, not necessarily a u substitution, but I can do a substitution on these to come up with one of our equivalent trig formulas, because cosine squared minus sine squared is actually the same thing as the cosine of 2x. So instead of cosine squared minus sine squared, that is the same thing as cosine of 2x dx. And then this is something that we can integrate. So this is going to be pi times the integral of cosine is going to be sine, because the derivative of sine is cosine. But remember, normally when I'm taking the derivative, I would have to multiply by 2. There is no 2 in front of this, so I'm going to have to put a 1/2 in there to deal with that. You could do a u substitution at this point, let the u be the 2x to go through and make that something so that it actually works. But again, the 1/2, that counteracts the chain rule that happens there. And so we're evaluating this from pi over 4 to 0. I'm going to extend this, give myself some more space. I am going to still keep that pi on the outside and deal with it at the end. And actually, I'm going to pull out the 1/2 as well. So this is going to become a pi over 2. And so I have the sine of 2 times pi over 4, which becomes pi over 2, minus the sine of 0. Well, the sine of pi over 2 is 1. Sine of 0 is 0. So I have pi over 2 times 1, which is simply pi over 2. And this is going to be units cubed. Pi over 2 units cubed. So that's the washer method. Anytime you have two different curves and they aren't solid in the middle, then you do have to do the outside disk minus the inside. Oh, I guess I'll hold off on that one. So this is where I'm going to stop for this first video. I thought that I had something on the previous page, but I think it's on the next page. I think it's still a page away. So I'll come back to that and cover that in the second video. Please go back through and rewatch these. Again, seek out other sources on the internet. There are some things with volumes that are not on the AP Calculus exam, including shells, and that's one of the things that I'm going to talk about in the second video. So just make sure that you are looking at material that is appropriate for the AB exam. Go back, rewatch this. And with everything else, please let me know if you have any questions.